The figure depicts a simplified model of the computer network, specifically an access network that provides connectivity between end system and the core network infrastructure. At the top of the figure, there are end systems including computers, smartphones, and other devices. These end systems are connected to the access network through their respective network interfaces. The access network is depicted in the middle of the figure and includes various physical components such as modems, routers, switches, and other network infrastructure. The access network provides the initial connection between the end system and the core network infrastructure. The core network infrastructure is represented at the bottom of the figure that includes various components such as routers, switches, and other networking equipments. The core network infrastructure is responsible for the routing traffic between different access networks, connecting end system to the servers, and providing access to the internet. In the figure, the access network is shown to be connected to the core network infrastructure via a high-speed link, which may be a fiber optical cable or high bandwidth connection. Overall, the figure demonstrates how an access network provides connectivity between the systems and the core network infrastructures, allowing for the transmission of the data between different devices and access to the internet.
In a client-server architecture, there is an always-on host called the server, which services requests from any other hosts called clients. A classic example is the web application, for which an always-on web server services requests from browser running on client host. When a web server receives a request from an object from a client host, it responds by sending the requested object to the client host. Note that with the client-server architecture, clients do not directly communicate with each other. For example, in the web application, two browsers do not directly communicate. Another characteristic of a client-server architecture is that the server has a fixed, well-known address called an IP address. Because the server has a fixed, well-known address, client can always contact the server by sending a packet to the server's IP address. Some of the better known applications with a client-server architecture include the web, FTP, telnet, and email. The client-server architecture is shown in figure 2.2a. Often in a client-server application, a single server host is incapable of keeping up with all the requests from clients. For example, a popular social networking site can quickly become overwhelmed if it has only one server handling all of its requests. For this reason, a data center housing a large number of hosts is often used to center a powerful virtual server. The most powerful internet services such as search engine, example Google and Bing, internet commerce like Amazon and eBay, web-based email, example Gmail and Yahoo Mail, social networking like Facebook and Twitter, employ one or more data centers. As discussed, Google has 30 to 50 data centers distributed around the world, which collectively handle search, YouTube, Gmail, and other services. A data center can have hundreds of the thousands of servers which must be powered and maintained. Additionally, the service providers must pay recurring interconnection and bandwidth cost for sending data from their data centers.
Peer-to-peer application. In a P2P architecture, there is a minimal reliance on dedicated servers in data centers. Instead, the application explores the direct communication between pairs of intermittently connected hosters called peers. The peers are not owned by the service providers but are instead desktops and laptops controlled by users, with most of the peer residing in home, universities, and offices. Because the peers communicate without passing through the dedicated servers, the architecture called peer-to-peer. Many of the today's most popular and traffic intensive applications are based on P2P architecture. These applications include file sharing, peer-assisted download acceleration, internet telephony, and IPTV. The P2P architecture is illustrated in the figure 2.2. We mentioned that some applications have hybrid architectures combining both client-server and P2P application elements. For example, for many instant messaging applications, servers are used to track the IP addresses of users, but user-to-user messages are sent directly between the user hosts. One of the most compelling features of P2P architecture is their self-scalability. For example, in a P2P file sharing application, although each peer generates workload by requesting files, each peer also adds services capacity to the system by distributing files to other peers. P2P architecture are most cost effective since they normally don't require significant server infrastructure and server bandwidth. However, further P2P applications face three major challenges. ISP friendly. Second one is security. Third one is incentives.
Figure 2.3 illustrates socket communication between two processes that communicate over the internet. Figure assumes that the underlying transport protocol used by the processors is the Internet's TCP protocol. As shown in this figure, a socket is the interface between the application layer and the transport layer within a host. It is also referred to as the application programming interface between the application and the network, since the socket is the programming interface with which network applications are built. The application developer has control of everything on the application layer side of the socket, but has little control of the transport layer side of the socket. The only control that the application developer has on the transport layer side is 1. Choice of the transport protocol, and 2. Perhaps the ability to fix a few transport layer parameters such as maximum buffer and maximum segment sizes. Once the application developer chooses a transport protocol, if the choice is available, the application is built using the transport layer services provided by that protocol.
HTTP request response behavior. When a user requests a web page, for example, clicks on a hyperlink, the browser sends HTTP request messages for the objects in the page to the server. The server receives the request and responds with HTTP response messages that contains the object. HTTP uses TCP as its underlying transport protocol rather than running on top of UDP. The HTTP client first initiates a TCP connection with the server. Once the connection is established, the browser and the server process access TCP through the socket interfaces as shown in the image.
Back of the envelope calculation for the time needed to request and receive an HTML file. Let's do a back of the envelope calculation to estimate the amount of time that elapses from when a client requests the base of HTML file until the entire file is received by the client. So we'll define the round trip time, which is RTT, which is the time it takes for a small packet to travel from a client to server and then back to the client. The RTT includes packet propagation delays, packet queuing delays in intermediate routers and switches, and packet processing delays. Now we'll consider what happens when a user clicks on a hyperlink. As we see in the figure, this causes the browser to initiate a TCP connection between the browser and the web server. This involves a three-way handshake. The client sends a small TCP segment to the server acknowledges and responds to the small TCP segment, and finally, the client acknowledges back to the server. The first two parts of the three-way handshake take an RTT. After completing the first two parts of the handshake, the client sends HTTP request message combined with third part of the three-way handshake into the TCP connection. So the one request message arrive at the server sends the HTML file into the TCP connection. This HTTP request or response eats up another RTT. So roughly the total response time is 2 RTTs plus the transmission time at the server of the HTML file.
HTTP message format. There are the two types, HTTP request message and the HTTP response message. Let's see the general format of the HTTP request message. HTTP message have the four section. First one is the request line and second one is the header line. Header line could be one or more than one, and after the header line we have the blank line, which is represented with the character carriage in the line field. Last one is the entity body. And let's see the request line has a three field. First one is the method, and second one is the URL, and third one is a version. The method, which is separated by the space character. After that we have the URL, which is separated by the space character, and third one is the version. After that the character carriage written in line field. Look at the example below. Method used here, the get method. Then there is a space here, some fold version. And let's see the header line. We have the four header lines. One is the header field name, so value here. See in the example, host is means header file name, the value of header line and the changed. Host means it is given the www my school education. After that, the connection close, it means after the sending the request, server can close the request. After the connection close, we have the user agent means the client is using, which is the browser. After the header line, we have the blank line. And after the last one is the entity body is empty because the get method is used here. Get method means get method is used when the browser requests an object with the request object identified in the URL. Thank you.
HTTP response message. Below we provide a typical HTTP response message. This response message could be the response to the example required message just discussed. This is a typical HTTP response. HTTP/1.1 indicates HTTP specification. 200 is HTTP status code. Content length basically indicates the number of characters within your message. Here it is 6821. The server is Apache/2.1 2.2.3. Content type basically indicates type of content that is easier for client to process it. Here content type is text/HTML. Let's take a careful look at the response message. It has three sections: an initial status line, 6 header line, and the entity body. The entity body is the meat of the message. It contains the requested object itself, represented by data, data, data. The status line has three fields: the protocol version field, a status code, and a corresponding status message. In this example, the status line indicates the server is using HTTP/1.1 and that everything is okay. Now let's look at the header line. The server uses the connection close header line to tell the client that it is going to close the TCP connection after sending the message. The date header line indicates the time and the date when the HTTP response was created and sent by the server. Note that this is not the time when object was created or last modified. It is the time when the server retrieves the object from the file system, inserts the object into the response message, and sends the response message. The server header line indicates that the message was generated by an Apache web server. It is analogous to the user agent. Header line in the HTTP request message. The last modified header line indicates the time and the date when the object was created or last modified. The last modified header, which we will soon cover in more detail in some for critical caching both in the local client and in the network cache server. Content length header line indicates the number of bytes in the object being sent. The content type header line indicates that the object in the entity body is HTML text. The content type header and not by file extension. Having looked up
an example, let us now examine the general format of the response message. The general format of the response message matches the previous example of the response message. The status code and associated phases indicates the result to the request. Some common status codes or associated phases include 200, OK, request succeeded and the information is returned in response. 301, moved permanently, requested object has been permanently moved. 400, bad request, this is a generic error code indicating that request could not understand by the server. 404, not found, the request document does not exist on this server. 505, HTTP version not supported, the requested HTTP protocol version is not supported by the server.
Hello guys, today we are going to discuss about cookies and how it works. In the above picture, let us take an example of Susan who always access the web using Internet Explorer from her home, and she contacts Amazon.com for a first time. Let us suppose that in the past she has already visited the eBay site. When the request comes into the Amazon web server, the server creates a unique identification number and creates an entry in its backend database that is indexed by the identification number. The Amazon web server then responds to Sushan's browser, including in the HTTP response a set cookies header, which contains the identification number. For example, the header line might be set cookies 1678 as shown in the figure. When Sushan's browser receives the HTTP response message, it sees the set cookies header. The browser then appends a line to special cookie file that it manages. This line includes host name of the server and the identification number in the set cookies header. Note that the cookies file already has an entry for eBay since Sushan has visited that site in the past. As Sushan continued to browse the Amazon site, each time she requests a web page, her browser consults her cookie file, extracts her identification number for this site, and puts a cookie header line that includes the identification number in the HTTP request. Especially, each of her HTTP requests to the Amazon server, including the header line cookie 1678. In this manner, the Amazon server is able to track Sushan's activity at the Amazon site. Although the Amazon website does not necessarily know Sushan's name, it knows exactly which page users 1678 visited, in which order, and what times. Amazon uses cookies to provide its shopping cart services. Amazon can maintain a list of all Sushan's intended purchases so that she can pay for them collectively at the end of the session. If Sushan returned to Amazon site, say 1 week later or 1 month later, her browser will continue to put the header line cookie 1678 in the request message. Amazon also recommends products to Sushan based on the web page she has visited at the Amazon in the past. This is how cookies are used by a website. Thank you.
Web caching. The browser establishes a TCP connection to the web cache, then sends an HTTP request for the object to the web cache. The web cache checks to see if it has a copy of object stored locally. If it does, the web cache returns the object within an HTTP response message to the client's browser. If the web cache does not have the object, the web cache opens a TCP connection to the origin server, that is to www.someschool.education. The web cache then sends an HTTP request for the object into the cache to server TCP connection. After receiving this request, the origin server sends the object within an HTTP response to the web cache. When the web cache receives the object, It stores a copy in its local storage and sends a copy within an HTTP response message to the client browser.
The figure we are looking at shows two networks, the institutional network and public internet. The institutional network is like a private high-speed internet just for the organization or institution using it. The institutional network is connected to the public internet through a link between routers on each network. On the internet, there are servers located all over the world that stores information that we access using our browsers. The institutional network generates an average of 15 requests per second to these servers. These requests are like little messages asking for information, and they are so small that they don't really affect the networks or link between them. When a request is sent, it takes a little while for the server to receive it, find the information, and send back to us. This time delay is called the internet delay, and it takes about 2 seconds on average for the server to send back the information we request.
Figure 2.13, adding a cache to the institutional network. Now consider the alternative solution of not upgrading the access link but instead installing a web cache in the institutional network. This solution is illustrated in figure 2.13. Hit rate, the fraction of requests that are satisfied by the caches, typically range from 0.2 to 0.7 in practice. For illustrative purpose, let us suppose that the cache provides a hit rate of 0.4 for this institution. Because the client and the caches are connected to the same high-speed LAN, 40% of the request will be satisfied almost immediately, say within 10 milliseconds, by the caches. Nevertheless, the remaining 60% of the requests still need to be satisfied by the origin server, but with only 60% of the requested objects passing through the access link, the traffic intensity on the access link is reduced from 1.0 to 0.6, typically a traffic intensity less than 0.8 corresponding to a small delay, say tens of milliseconds on a 1.5 Mbps link. This delay is negligible compared with 2-second internet delay. Given this consideration, average delay therefore is 0.4 into 0.01 second plus 0.6 into 2.01 second, which is just slightly greater than 1.2 second. Thus, this second solution provides an even lower response time than the first solution, and it doesn't require institution to upgrade its link to the internet. The institution does of course have to purchase and install a web caches, but this cost is low. Many caches use the public domain software that run on the inexpensive server and the PCs. Through the use of content distribution network, web caches are increasingly playing an important role in the internet. A CDN company install many geographical distributed caches through the internet, thereby localizing much of the traffic. There are shared CDN and the dedicated CDN.
The most common task expected nowadays in a network link is transferring a file from one computer to another computer. The greatest volume of data exchanged in the internet today is due to the file transfer. Now let us see about FTP, means File Transfer Protocol. FTP is an application layer protocol that moves files between local and remote file system. FTP works on client-server model. User interacts with FTP through an FTP user agent. FTP client is a program that runs on the user's computer to enable the user to talk to and get files from the remote computers. Set of FTP commands that establishes the connection between user and server. Once the server has authorized the user can transfer the files or copies one or more files in local file system into remote file system. Then it closes the connection. FTP session is started between client and server. The client initiates a control TCP connection with server side. The client sends control information over this. When the server receives this, it initiates a data connection to client side. Then only one file can be sent over one data connection, but control connection remains active throughout the user session. FTP needs to maintain a state about its user throughout the session.
Now let us see about two types of connection in FTP. The most striking difference is that FTP uses two parallel TCP connection to transfer a file, which is nothing but control connection and data connection. In control connection, it is used for sending control information between two hosts, such as user identification, password, commands to change remote dictionary, and commands to put and get files. It uses a very simple rules for communication. Then we can transfer a line of commands or responses at a time, which remain connected throughout entire FTP session. So basically in control connection, you will be transferring only commands or texts based on things. Whereas in data connection, you can transfer very complex data representation and all those things. The data connection is actually send a file because FTP uses a separate control connection, which means FTP is said to send its control information out of band. So the data connection uses very complex rules as data types and it may vary, like opens and close and transfer the files. HTTP sends requests and response header lines into same TCP connection that carries the transfer file itself. For this reason, HTTP is said to send its control information in band. The FTP control and data connections are illustrated in figure 2.15. When the user starts an FTP session with a control host, the client side of FTP first initiates the control in TCP connection with the server side. Then, the client side of the FTP sends the user identification and password over this control information. Then, when a server side receives a command for the file transfer over control connection, FTP sends exactly one file over the data connection and then closes that data connection. Thus, with FTP, the control connection remains open throughout the duration of the user session, but at the same time, new data connection is created for each file transfer within a session. The commands from a client to server and replies and from server to clients are sent across a control connection in 7-bit ASCII format. Each command consists of 4 uppercase ASCII characters, some with optional arguments. Some of the more common commands are username and password, which are used to send the user identification and user password to the server. List is used to ask the server to send back a list of all files in the current remote dictionary. Retrieve file name used to retrieve a file from the current dictionary of the remote host. Store file name used to store a file into a current dictionary of the remote host. Some typical replies along with the possible messages are 331 username OK, password required, 125 data connection already open, which is transfer starting, 425 can't open data connection, 452 error writing file. The other FTP commands and replies are encouraged to read RFC 959.
High level view of the Internet Mail System. We see from this diagram that it has three major components: user agents, mail servers, and the simple mail transfer protocol. We now describe each of these components in the context of a sender, Alice, sending an email message to a recipient, Bob. User agents allow users to read, reply to, forward, save, and compose messages. Microsoft Outlook and Apple Mail are examples of user agents for email. When Alice is finished composing her message, Our user agent sends the message to our mail server where the message is placed in the mail server's outgoing message queue. When Bob wants to read a message, his user agent retrieves the message from his mailbox in his mail server. Mail servers from the core of the email infrastructure. Each recipient, such as Bob, has a mailbox located in one of the mail servers. Bob's mailbox manages and maintains the messages that have been sent to him. A typical message starts its journey in the sender's user agent, travels to the sender's mail server, and then travels to the recipient's mail server where it deposited in the recipient's mailbox. When Bob wants to access the messages in his mailbox, the mail server containing his mailbox authenticates Bob with usernames and password. Alice's mail server must also deal with failures in Bob's mail server. If Alice server cannot deliver mail to Bob's server, Alice server holds the message in a message queue and attempts to transfer the message later. Reattempts are often done every 30 minutes or so. If there is no success after several days, the server removes the message and notifies the sender Alice with an email message. SMTP is a principal application layer protocol for the Internet Electronic Mail. It uses the reliable data transfer service of TCP to transfer mail from the sender's mail server to the recipient's mail server. As with most application layer protocols, SMTP has two sides, a client side which executes on the sender's mail server and a server side which executes on the recipient's mail server. Both the client and the server sides of SMTP run on every mail server. When a mail server sends mail to other mail servers, it acts as an SMTP client. When a mail server receives mail from other, other mail servers, it acts as SMTP server.
Number 2.17, Alice sends a message to Bob. The scenario is summarized in figure number 2.17. It is important to observe the SMTP does not normally use the intermediate mail server for sending mail. Even when the two mail servers are located at opposite ends of the world, if Alice server is Hong Kong and Bob server is St. Louis, the TCP connection is direct connection between the Hong Kong and the St. Louis servers. In the particular Bob's mail server is down, the message remains in the Alice mail server and wait for the new attempt. The message does not get placed in the some intermediate mail server. Let's now take a closer look at the how SMTP transfer of a message for the senders sending the email server to the receiving mail server. We will see the SMTP protocol has many similarities with the protocol that are used to face-to-face human interaction. First, the client SMTP running on the sending email server host has TCP establish a connection to port 25 at the server SMTP running on the serving and receiving host. The server is down, the client tries to start again. Once the connection is established, the server and client perform some application layer handshaking just as humans, often introducing themselves before transferring information from one to another. SMTP clients and servers introduce themselves before transferring information. During this SMTP handshaking phase, the SMTP clients indicate the email addresses of the senders and the email addresses of the recipient. When the SMTP format client servers had introduced themselves to each other, the client sends a message. SMTP can count on the reliable data transfer service of TCP to get the message to the server without errors. The client then repeats this process to the same TCP connection. If it has other message to send to server, otherwise it instructs TCP to close the connection. Let's next take a next step, look at the example of transcription of the message exchanged between SMTP client C and SMTP client server S. The host name client creps.fr and the host name server is hamburger.edu. The ASCII text lines preceded like with C dot colon are exactly the lines of the client sends into the TCP socket, and the ASCII text lines preferred with S semicolon are the lines exactly the server sends to the TCP socket. The following transcription begin to the all the TCP connections are established. In the above example, the client sends a message, "Do you like ketchup? How about pickles?" For the mail server crepes.frfr to the mail server hamburger.edu. As part of the dialog, the client issued the five commands: hello, an abbreviation of hello, mail from, receipt to, data, and quit. These commands are self explanatory. The clients also send the line of consisting of single period which indicates the end of the message of the servers. The server issues replies to the command, each command with the each reply having a reply code of some optional language explanation. We mentioned here the SMTP uses persistent connections in the sending mails and servers to the has connections. Message to send the same receiving to the mails. It can be sent all message over the same TCP connection for the each message. The client begins the process with a new mail for from designated the end to the is isolated period and issues quit only after the all messages sent. It is highly recommended that telnet to carry out the direct dialogue with an SMTP server to this issue. Telnet server where the server name is name of the local mail servers. When they do the you are simply establishing a TCP connection between your local host and mail server. After typing this line, you should immediately receive the 220 replies off from the server. Then issue the SMTP commands: hello, mail from receipt to, data, clarif and quit to approximate times. It is also highly recommended than the programming assignment 3 at the end of the chapter. In the assignment, you will build a simple user agent in the implementation of client-side SMTP. It will allow you to send emails and send attributes received via local mail server.
In email protocols and their communicating entities, Alice's user agent uses SMTP to push the email message into her mail server. Then Alice's mail server uses SMTP to relay the email message to Bob's mail server. Primarily because without relaying through Alice's mail server, Alice's user agent doesn't have any resources to an unreachable destination mail server. By having Alice first deposit the email in her own mail server, Alice's mail server can repeatedly try to send the messages to Bob's mail server, say every 30 minutes, until Bob's mail server becomes operational. The SMTP RFC defines how the SMTP commands can be used to relay a message across multiple SMTP servers. The Bob's user agent can't use SMTP to obtain the messages because obtaining the messages is a pull operation, whereas SMTP is push protocol. The puzzle is completed by introducing a special mail access protocol that transfers messages from Bob's mail server to his local PC. There are currently a number of popular mail access protocols, including Post Office Protocol version 3, that is POP3, Internet Mail Access Protocol IMAP, and HTTP. This diagram shows summary of the protocols that are used for internet mail. SMTP is used to transfer the mail from sender mail server to the recipient mail server. A mail access protocol such as POP3 is used to transfer mail from recipient mail server to the recipient user agent.
DNS server. The DNS uses a large number of servers organized in a hierarchical fashion and distributed around the world. No single DNS server has all of mappings for all of the hosts in a internet. Instead, the mappings are distributed across the DNS server. In these three classes of DNS server: root DNS server, top level domain DNS server, and authoritative DNS server, organized in a hierarchy as shown in a figure. First one, root DNS server. Root name servers provide the IP address of TLD servers. Hundreds of root name servers are managed and maintained by tens of organized all over the world. Second one, top level domain servers. For each of the top level domains, there is TLD servers. Example, tldr.com, .org, .pk.uk. TLD servers provide the IP address for authoritative DNS servers. Third one, authoritative DNS server. Every organization with publicly assembly host on internet must provide publicly assembly DNS records that map the names of those hosts to IP address. An organization can choose to implement its own authoritative DNS server to hold these records. Alternatively, the organization can pay to have these records stored in an authoritative DNS server of some service provider.
Interaction of the various DNS servers. In figure 2.21, make use of both recursive queries and iterative queries. The query sent from sys.poly.edu to dns.poly.edu is the recursive query, since the query asks dns.poly.edu to obtain the mapping on this behalf. But the subsequent three queries are iterative, since all the replies are directly returned to dns.poly.edu. In theory, any DNS query can be iterative or recursive.
If we take a look at figure 2.22, we can see a chain of DNS queries that all are recursive. This means that each DNS server in the chain is responsible for finding the answer to the queries itself and then passing that answer back to the previous server in the chain, all the way back to the requesting host. However, in practice, DNS queries tend to follow a different pattern, which is shown in the figure 2.21. The initial queries from the requesting host to the local DNS server is still recursive, meaning the local DNS server is responsible for finding the answer, but remaining queries in the chain are iterative, meaning that each server in the chain provides the address of the next server to the query until the final server provides the answer back to the local DNS server, which then pass it back to the requesting host.
DNS message format. The first 12 bytes is the header section, which has a number of fields. The first field is a 16-bit number that identifies the query. This identifier is copied into the reply message to a query, allowing the client to match received reply with the sent queries. There are number of flags in the flag field. A 1-bit query or reply flag field indicate whether the message is a query 0 or a reply 1. A 1-bit authoritative flag is set in a reply message when a DNS server is an authoritative service for a queried name. A 1-bit recursion desired flag is set when a client or a host or DNS server desire that the DNS server perform recursion when it doesn't have the record. A 1-bit recursion available field is set in a reply if the DNS server supports recursion. In the header, there are also four number of fields. These fields indicate the number of occurrence of the four type of data sections that follow the header. The question section contains information about the query that is being made. This section includes 1. A name field that contains the name that is being queried, and a type field that indicates the type of question being asked about the name. In a reply of a DNS server, the answer section contains the resource record for the name that was originally queried. The authoritative section contains records of other authoritative servers. The additional section contains other helpful records. Inserting records into the DNS database. Suppose you have just created an existing new startup company called Network Utopia. The The first thing you will want to do is register the domain name networkutopia.com at a registrar. A registrar is a commercial entity that verifies the uniqueness of the domain name, enter the domain name into the DNA database, and collects a small fee from you to its servers. For the primary authoritative servers for networkutopia.com, the registrar would insert the following two resource records into DNS server system: networkutopia.com, dns1.networkutopia.com, commonness, peer-to-peer applications. In P2P architecture, there is a minimal or no reliance on always on infrastructure servers. Instead, pairs of intermittently connected hosts called peers communicate directly with each other. P2P file distribution. In P2P file distribution, each peer can distribute any portion of the file it can receive to any other peers, thereby assisting the server in the distribution process. The most popular P2P file distribution protocol is BitTorrent.
Let us first determine the distribution time for the client-server architecture, which we denoted by D by CS. In the client-server architecture, none of the peers adds in the distributing the file. We can make the following observation. The server must transmit one copy of the file to each of the n peers. Thus, the server must transmits nf bits since the server uploads rate is u raised to 5. The time to distributing the file must be at least nf by u by s. Let dmin denote the download rate of the peer with the lowest download rate. That is d min equal to min bracket open d1 comma dp to dn bracket close. The peer with the lowest download rate cannot obtain f bits of the file in least of the f by d minimum second. Thus the minimum distribution time at least f by d minute. Putting these two observations together, we obtain d raised to cs is greater than or equal to max of bracket open nf by us and f by d minimum. This provides a lower bound on minimum distribution time for the client-server architecture. In a homework problem, you will be asked to show the server can schedule its transmission so that the lower bound is actually achieved. So let us take its lower bound provide above the actual distribution time, that is dcs equal to max bracket open nf by us comma f by t is to min. We see from the equation 2.1 that the n large enough, the client-server distribution time is given by nf by us. Thus, the distribution time increases linearly in the number of peers n. So, for example, if the number of peers from 1 week to next increase, thus the thousandfold from the thousand to million, the time required to distribution the file also the peer increase by thousand. Let's now go through the similar analysis for P2P architecture, where each peer can assist the server in distributing the file. In particular, when the peer receives some file data, it can use it for own upload capacity to redistribute the data to other peers. Calculating the distribution time for the P2P architecture is somewhat more complicated than the client-server architecture since the distribution time depends on how each peer distributes point position for the file to the other peer. Never this is the simple expression of the minimal distribution time that can be obtained. At the beginning of the distribution, only the server has the file. To get this file into the community of peer, the server must send each bit of file at least once into the access link. Thus, the minimal distribution time in at least f by us, unlike the client server scheme, but a bit sent once by the server may not have to send the server again. The peers may have redistributed the bits among themselves. As with the client-server architecture, the peer with the lowest download rate can obtain all f bits on the file is less than f by d minimum second. Thus, the minimum distribution of the time is at least f by d minimum. Finally, observe the total upload capacity by the system as a whole is equal to the upload rate of the server plus the upload rates of each of the individual peer, that is u total equal to us plus u1 plus raised u plus u raised to n. The system must deliver f bits to each nodes of the n peers, thus delivering a total nf bits cannot be done at this rate faster than u total. Thus, the minimum distribution time is also at least nf by u by s plus u by 1 plus till u raised to n. Putting these three observations together, we obtain the minimum distribution time for P2P denoted by dP2P, where dP2P is greater than or equal to max of f by us, f by d min, and f by us plus sigma of ui, where I is equal to 1 raised to n. Equation 2.2 provides a lower bound for the minimal distribution time for the P2P architecture. It turns out when we imagine that each peer can redistribute a bit as soon as it receives the bit, then there are redistribution schemes that actually achieve the lower bound. We will prove a special case of this result in homework. In reality, p chunks of the file are redistributed rather than individual bit. Equation 2.2 serves a good approximately an actual minimal distribution time. Thus, let's take a lower bound provided by the equation 2.2 as a actual minimum distribution time, that is dp2p equal to max of f raised to us, where d raised to d by minimum and nf divided by us plus sigma of ui, where I is equal to 1 to n. Figure 2.2.5 compares the minimum distribution time of the client server and the P2P architecture, assuming that all prayers have the same upload rate u. In the figure 2.25, we have all set f by u equal to 1 hour, us equal to 10 units, and d min is greater than or equal to us. Thus, the peer can transmit the entire file on 1 hour. The server transmission rate is 10 times the peer upload rate. For the peer download rates, it's set larger enough for that is not to have an effect. We see from the figure 2.25 that for the client server architecture, the distribution time increasingly linear and without bound as the number of the peers increases. However, for the P2P architecture, the minimum distribution time is not only always less than the distribution time on the client server architecture, it is also less than an hour for a number of peers n. Thus, the application with P2P architecture can be self-scaling. This scalability is directly consequences for the peer ping distribution as well as the consumer of the bits.
Figure 2.25 Distribution time for P2P and client server architectures. In figure 2.25 compares the minimum distribution time for the client server and P2P architecture, assuming that all peers have the same upload rate u. In figure 2.25 we have set f bar u is equal to 1 hour. So us is equal to 10u and distribution minimum just greater than or equal to us. Thus a peer can transmit the entire file in 1 hour. The server transmission rate is 10 times the peer upload rate, and for simplicity, the peer download rates are set large enough so not have an effect. We see from figure 2.25 that for the client server architecture, this distribution time increases linearly and without bound as the number of peers increases. However, for the P2P architecture, the minimal distribution time is not only always less than the distribution time of the client server architecture, it is also less than 1 hour for any number of peers of n. Thus, applications with the two peer-to-peer architecture can be self-scaling. This scalability is direct consequence of peers being redistributors as well as the consumer of the bits.
Hello. And to determine which request she responds to BitTorrent uses a clear training algorithm. The basic idea is that Alice gives priority to the neighbors that are currently supplying her data at the highest rate. Specifically for each of her neighbors pairs that feeding her bits at the highest rate, she then records by sending chunks to these same 4 pairs. Every 10 seconds she recalculates the rates and possibly modifies the set of 4 pairs. In BitTorrent lingo, these 4 peers are said to be unlocked importantly every 30 seconds. She also picks one additional neighbor at a random and sends it chunks. Let's call the randomly chosen peer Bob. In BitTorrent lingo, Bob is said to be obstinately unchoked because Alice is sending a data to Bob. She may become one of Bob's top 4 uploaders, in which case Bob would start to send to Alice. If the rate at which Bob sends data to Alice is high enough, Bob could then in turn become one of Alice's top 4 uploaders. In other words, every 30 seconds, Alice will randomly choose a new trading partner and initiate trading with that partner. If the 2 peers are satisfied with the trading, they will put each find a better partner. The fact is that peers capable of uploading at compatible rates tend to find each other. The random neighbor selections allows new peers to get chunks so that they can have something to trade. All other neighboring peers besides these 5 peers, that is, they do not receive any chunks from Alice. BitTorrent has a number of interesting mechanisms that are not discussed here, including pieces, mini chunks, pipelining, random, first selection, endgame mode, and anti-snubbing. The incentive mechanism for a trading just described is often referred to as tit for tat. It has been shown that these incentive schemes can be circulated, but the BitTorrent ecosystem is widely successful with billions of simultaneous peers actively sharing files of 100 of torrents. If BitTorrent has been designed without tit for tat but otherwise exactly the same, BitTorrent would likely not even exist now, as the majority of users would have been interesting variants of the BitTorrent protocol are proposed.